In this video, we're going to talk about some recursive definitions, and then in the next video, we'll finish with structural induction. But right now, we're going to focus on what recursive is. We've talked about it previously, recursive sequences in particular, and here I pulled up the definition right here. So a recursive sequence uses an equation that expresses a sub n in terms of one or more of the previous terms of the sequence. So it's a way of producing terms in the sequence by using the previous terms to do it. A famous example that we looked at was the Fibonacci sequence, and we just kind of defined it and left it at that. But I'm bringing it back up because we're going to talk about it again today. The Fibonacci sequence is so special, it gets its own labels, f sub 0, f sub 1, f sub 2, where f sub 0 is 0, f sub 1 is 1. And each next term, f sub n, is defined by the previous term, n minus 1 plus n minus 2. So I'm going to write out then what the terms are going to look like. So f sub 2, which is the next term in this sequence, is based on f sub 0 and f sub 1, adding those two terms, which would be 1, right? And then f sub 3 would be based on adding up. Oops, sorry, that's a sad looking 3. Let me fix it. F sub 3, there we go, is based on adding up f sub 2 and f sub 1, which means we're going to add up 1 plus 1, which is 2. F sub 4 is based on adding up f sub 2 and f sub 3, which is 3. And so forth. So the idea is we keep going, we keep adding the two previous terms, and that produces the next term in the sequence. So if I wanted to write this as a function, it's possible. We have two things that we have to do, and we technically did it on the recursive sequence too. We just didn't quite look at it like this. We had the basis step and the recursive step. The basis step kind of starts with our basic value. In the Fibonacci sequence, the basis step was defining f of 0 and f of 1. I'm sorry, f sub 0 and f sub 1. So by defining those two, they gave us the basis of where to start. And then they gave us the formula for how you produce the next term. You add up the two previous terms, okay? So the recursive step is give a rule for finding its value in an integer form, and its values based on smaller integers. So let's look at an example of this. It's going to be very similar to sequences. We start with f 0 equals 3. That is like our basis step here, okay? And then we give the recursive step. This is the formula. So each new term is produced by doing 2 times f of n plus 3. So they ask us to find f of 1. So let's do that. F of 1 then is, so 1 is what we're plugging in for n plus 1. So n in this case is 0. Because the previous term for f of 1 was f of 0. Our starting term was f of 0. So we're going to be finding 2 times f of 0, the previous term, plus 3. It doesn't look like a 0, but there we go. Oh, man, I just made it worse. We're going to fix it because I don't want it to be confusing. There we go, f of 0 plus 3. Okay, well, f of 0 is 2 times 3 plus 3, which is 6 plus 3 is 9. Okay, cool. F of 1 is 9. Now let's find f of 2. F of 2 is 2 times f of 1 plus 3, so the previous term, which in this case is 2 times 9, because that's the previous term, plus 3, so that's 18 plus 3 is 21. All right. F of 3, so that's 2 times f of 2 plus 3, which is 2 times 21 plus 3, so that's what? 42 plus 3 is 45. And then lastly, f of 4 is 2 times the previous term, which is f of 3 plus 3 is 2 times 45, which comes out to 90 plus 3 is 93. And there we go. All the terms of our function. Very similar to how we did the sequences before. Okay, let's create a recursive definition. So they're telling us to create a recursive definition for f of n factorial. So n factorial is first term would be the 1 factorial. So that would be our first term of our function. So we want to give a basis step for that. The next term would be finding 2 factorial, and then 3 factorial, and then 4 factorial, and so forth, okay? So remembering, the very first term is going to be a 1. The next term is produced as 1 times 2. The next term is produced as 1 times 2, 1 times 2 times 3. The next term is 1 times 2 times 3 times 4. All right, and it keeps going. So every term, we're adding a new term at the end, and it's all the previous terms times a new term at the end. All right, and that term does match what we are taking the factorial of. Okay, so let's use that to create our definition. So let's start with the basis step. So the basis step for us is we want to say that the very first term is going to come out to 1, which happens to be 1 factorial. Okay, then for the recursive step, oops, there's an I there. Recursive step, we're going to say that the next term, whatever that looks like, is going to be the previous term times the next term. Right? What I just did over here, the fact that if I'm finding n plus 1 factorial, I'm multiplying by n plus 1. So let's test this out. Let's make sure it works here. Let me do it in green. So let's say I want to see if I get f of 2 correct. So f of 2 means that I'm taking 2 and I'm timesing it by the previous one, which is 1. Boom, that works. Okay, now let's check f of 3, just to be certain. So f of 3 says I take 3 and then I times it by the previous term, which is 2 plus, well, sorry, technically just 2, which came from 2 times 1. And that gave me 6. And then f of 4 is 4 times the previous term, which is 6, and that comes out to 24. But 6 was formed by 3 times 2, and the 2 was formed by 2 times 1. And so it is forming a factorial because each time I'm multiplying by the new term. So yay, we did it. Okay. Now let's look at a sequence. We can do this with sequences too. If I want to give a recursive formula for this sequence, so let's just kind of see. This sequence starts with 0, so a sub 0 is the first term, and it's a sum. So then I'd add to it a sub 1, and then a sub 2, and then a sub 3, and dot, 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 right? It keeps going forever. I just keep adding until I get to a sub n. All right. So if I want to do a basis step, the basis step is going to be the very first term, which means I just want the a sub 0 term. So k is going to go from 0 to 0. That's how I get a single term to pop out. So a sub k equals a sub 0. And we're done. There's the first term, the basis step. Okay, now the recursive step is a little funny here. Because what we want to do is we want to take the next term that would be produced in this sequence, or sum, series is what they call this, a series. So I want to go from k going from 0 to n plus 1, not just n, right? N plus 1. And what I want to do is I want to take all of the terms that were prior to it, all of the sum from k sub 0 to n. So I'm taking that series, and then I'm going to add a sub n plus 1. Oh, I'm so sorry. My email is open, and I apologize. Let me just close that out right now. Okay, cool. Now that we won't hear that dinging anymore, and I apologize for that. So this defines the next term if I wanted to take this sequence a step further. If I wanted to go out beyond n and go to n plus 1, I would need to add on an a sub n plus 1, a new term based on the n plus 1 place value. That's how the recursive definition works. Okay, we're going to do a proof now. This particular proof kind of ties together strong induction and the recursive definition, in particular of the Fibonacci sequence. So this f sub n is based on the Fibonacci sequence that we saw earlier. So that is Fibonacci. Okay, so it's Fibonacci's numbers of the terms. All right. And then this is alpha to the n minus 2, where alpha is defined to be this specific number. Now, I'm going to make a note of where this came from. In the proof, we note where it is, but it's kind of like, where the hell did this weird number come from? So this number came from, it's a solution to the equation x squared minus x minus 1 equals 0, which we'd have to solve using the quadratic formula or completing the square. And it would give you two answers, and this is one of the answers, the positive answer, okay? If you were to plug this number into your calculator, if you were to grab your calculator and plug it in, it comes out to about 1.618. 1.618. So it's under 2. We get less than 2 when we plug this into the calculator. That actually makes sense because the square root of 5 is a little bigger than the square root of 4. So this comes out to 2 point something, right? And if I do 1 plus 2, which is 3, and then divide it by 2, that's approximately 1.5. So I could have kind of figured that out without really plugging into the calculator. It's about 1.5. It's technically bigger than 1.5, simply because I rounded the square root of 5 to be like the square root of 4. All right. But there you go. That's how they get this magic number from solving this quadratic equation. That does come into the proof. All right. But let's start by proving this. So because we're talking about a statement that n is bigger than or equal to 3 whenever that happens, f sub n, that Fibonacci number is going to be bigger than alpha to the n minus 2, where alpha happens to be this magic number here. Okay, so let's create a proposition. Let's let P of n be the proposition that f sub n does come out bigger than alpha to the n minus 2. So alpha kind of looks like a little bit of a fish. All right, mine sometimes looks like a incomplete 2. So I apologize. I'll do my best to try to make alpha as distinct as I can. That's alpha. Okay, we're going to use strong induction, which we learned in the last section. And first thing I'm going to do is I'm actually going to show that P of 3 works. And for reasons you don't know, I'm going to also show that P of 4 works. Actually, no, it makes sense. Fibonacci sequence is based on the two previous terms, right? The Fibonacci sequence. So I really should start with the first 2 terms of this proposition, what happens at 3 and what happens at 4. Okay. So P of 3 and P of 4 are true. And the reason they're true is P of 3 is based on the Fibonacci number f of 3, which we calculated earlier. If you go back and look at that, it happened to be 2. And that is bigger than alpha to the 3 minus 2, which is 1. And alpha to the 1 is approximately 1.6 or 1.5. So this is definitely bigger than alpha. Okay. So we're done. Cool. That one's done. And f sub 4, here, I want to put in here that this happens to be alpha is bigger than 1.5. I'm just going to write that down up here. Okay. F of 4 is 3, which again, we found earlier. We can go look at that. And 3 is going to be bigger than alpha to the 2, alpha squared. So if I square 1.5, it doesn't come out to 3. It comes out to like 2 point something. So yeah, that works. Now you can take this number 1 plus the square root of 5 divided by 2, plug into your calculator and be like, okay, this is 1.6. So clearly 2 is bigger than 1.6. You can do that. There's nothing wrong with it. But often when we do formal proofs in math, we don't like to write down decimal approximations. We like to base it on theory. And the theory is that this number alpha is bigger than 1.5. Okay. This comes out to like 2.6 something. All right. So just so you know, you could plug into the calculator. It'll work. We're a calculator generation, so we like our calculators. But this is an old type of math prior to calculators. So they didn't care so much about the actual numbers. They cared more that it was going to work for the inequalities. Okay, so let's assume, using strong induction, we assume all the previous cases work. So assume P of J is true, where J is, hold on, I'll say that, namely f sub j is bigger than alpha to the j minus 2 for all integers j that is between 3 and k. That is an equal to sign. There we go. Okay. And we're letting, at the moment, because we have shown P of 3 and P of 4, we're really talking about numbers bigger than that. So at least from k equals 4 and bigger. All right, because we kind of already showed those in our basis step. All right, so let's consider the case we're trying to prove, which is P sub k plus 1. Or I'm sorry, P of k plus 1. K plus 1 case. That means we're trying to show, we want to show that f sub k plus 1 is bigger than alpha. Okay, so if this is n minus 2, if I plug in k plus 1, that becomes k plus 1 minus 2 or k minus 1. So this is what I'm trying to show is true. This is what I want to show is true. All right, so here's what I got to do. I got to tackle a way of looking at the Fibonacci numbers in terms of alpha. So let's start by bringing up what I said they were going to bring up in the proof. And that is, we know, or alpha is a solution to x squared minus x minus 1 equals 0, which means that we could rewrite this in terms of alpha, plugging alpha in for x, and it would be alpha squared minus alpha minus 1 equals 0. Or another way of saying that is alpha squared equals alpha plus 1. All right, so I'm taking and I'm solving it for the squared term. Okay, that means then that alpha to the k minus 1, which is what I'm trying to get at right now, right? Alpha to the k minus 1. Sorry, that kind of looks like an A, but it's alpha. Alpha to the k minus 1 happens to equal, if I take off a squared, alpha squared times alpha to the k minus 3. All right. Now, the reason I'm doing that is I'm going to pull in the information I had previously. The previous information I had that I'm trying to pull in is that f sub j is bigger than alpha to the j minus 2. Now, I overshot a little bit. I went to j minus 3, quote unquote. I'm using k, but because I have to do the previous two terms. Okay, so that's why I did that. All right, now here I'm going to use my magical statement that I just said right over here. I said that alpha squared equals alpha plus 1, and I just produced alpha squared, which is what I wanted. So this is going to equal alpha plus 1 times alpha to the k minus 3. Cool. Also, I wanted to introduce alpha squared here. Okay, I wanted to do that. So that's in order to do that, it had to be alpha to the times k minus 3. Okay, now I'm going to distribute that. So that's alpha times alpha to the k minus 3 plus alpha to the k minus 3. And looky here, alpha times alpha to the k minus 3 is alpha to the k minus 2 plus alpha to the k minus 3. So those are the two previous alphas. Look at that. Look, it's in the form of like a recursive sequence. I started with alpha to the k minus 1, and I'm showing that it is the addition of the two previous alphas of the powers. Okay, that's useful because I want to backtrack now and bring in the Fibonacci numbers. So by our assumption, I did notice, by the way the book words this particular phrase, by our assumption, they usually say by the recursive definition or by our induction step. Like sometimes they say that. They refer to what we have claimed. I just say by assumption because I feel like we use the word assume and it feels like it's telling you to go back to look at what we assumed. So by our assumption, since k is bigger than or equal to 4, then we can say that f sub k must be bigger than alpha to the k minus 2, and f sub k minus 1 is bigger than alpha to the k minus 3. So I'm giving Fibonacci numbers for each of these alphas I've just created over here, these two alphas over here. All right, I don't know if you heard my dog wiggling in the background, but sorry for that noise. All right, here, we're almost done. So f sub k plus 1 is going to be based on the Fibonacci number, the two previous Fibonacci numbers. But these two previous Fibonacci numbers happen to be bigger than these two alpha values, k minus 2 and k minus 3. However, those two alpha values up here, we showed those two alpha values, alpha k minus 1 equals those two alpha values. We showed that. So these actually equal alpha to the k minus 1. And we did it. We showed that f sub k plus 1 is bigger than alpha to the k minus 1, which is what we wanted to show up here. We stated that when we said consider p sub k. We did it. Yay. So p of k plus 1 is true. And we have proved it using strong induction. Okay, now from here, the book introduces Lemay's theorem. I think it's Lemay's theorem. Lemay's theorem says, let a and b positive integers with a bigger than or equal to b, then the number of divisions used in the Euclidean algorithm to find the GCD of a, b is less than or equal to the number of decimal digits in b. And it uses what we just showed in this theorem, which is why they bring it up. They're showing an application of what we just did here. So the proof is in the book, and you are welcome to go look at it if you would like to. We're going to go ahead and look at recursively defined sets, and then we'll pause after that. In the next video, we'll pick up with recursively defined strings. But let's start with recursive definition of sets. So here's the two parts. The basis step is the initial collection of elements, so whatever elements we need to start with, and then the rules for finding new elements that are going to be in the set. Okay. Now, this is an important statement. Note, the recursion definition has an exclusion rule sometimes, which specifies that the set contains nothing other than the elements listed in the basis step. All right. Now, this is the important thing I want to note. We will always assume the exclusion rule holds, meaning whatever they tell us in the basis step, we're going to assume that that's what's in the set to start with. And we're not going to assume other things are there. We're going to start with that and use that until we're able to show anything else. Okay. For example, let's say we have this integer set S, and I'm told that 3 is in the set. So all I know is that 3 is in that set. So that's what I'm going to work with here. So if X happens to be in the set and Y happens to be in the set, then X plus Y is in the set S. So what I know is, since 3 is in the set, I can say that 3 plus 3 must be in the set, because I can let X be 3 and Y be 3 because I know 3 is in the set, which now means that 6 is in the set. So I've just found another element in the set. So now that I have two different elements in the set, 3 and 6, 3 plus 6 must also be in the set S. And I can keep producing elements this way. You might notice that because I'm basing this on 3, I'm going to end up getting multiples of 3, and we'll see that in a later example. All right, let's look at this set here. The natural numbers. If I want to define the natural numbers, n, the basis is to say that 0 is an element of n. Now, some books actually don't assume n to be the containing 0. A lot of them will call it the whole numbers. So just so you're aware, this book is assuming the natural numbers do start at 0. Okay, so if n is in the natural numbers, then n plus 1 is in the natural numbers. So if we happen to know something's in the natural numbers, then the next integer is going to be in the natural numbers too. So since we know 0 is in the natural numbers. I'm going to use the double bracket label. Then the next number in there is going to be 1 because 0 plus 1 is going to be in the natural numbers. And then because I know 1 is now in the natural numbers, then the next number is going to be in there, which is 2. And the pattern continues. So the idea is that we can produce the new numbers based on one piece of information, and we will base it on the one piece of information they've given us. Sometimes they give us more information, but we will always assume that's all we know. And then we'll continue this discussion on strings in the next video.